Good morning, everybody. Happy you're here today, and I'm going to talk today about the present and the future of high-temperature polymers. Trying to get out of the mic. Well, so maybe just a brief introduction who I am. My name is Stephanie, and I have been with EOS for 5 years, and just end of last year transferred to the US from Germany, and I now focus on business development for the high-temperature polymers. So that's why I have the honor to speak today about this topic. Before we go into details, let me give you a brief overview. So EOS was founded in 1989. That's approximately 30 years ago, more or less the time when 3D printing was born. And for a very long time, prototyping had been the leading application field. Our customers were early adopters, and in terms of what we saw as AM technologies that are offered on the market, they all had a kind of limited purpose portfolio. And as of today, we already see certain applications, selected parts that are in production. And we do see a lot of applications that are being qualified for production. When we look at our customer interface, it's more the R&D departments of big established corporations. And when we look at what is offered to the market, it's a general purpose portfolio. Now, moving on, in the near future, it will move all more and more to production. So all those parts that are being qualified for production today will actually be ramping up. We will see significant increase in production of final parts. Our customer interface, again, is changing more to the production departments of established companies. And in terms of what we offer to the market, it will be more specialized, it will be more addressing the needs that come along with production. So anything around quality assurance, automation, that's the things we're currently working on and that will come to market. If you have that in mind, if you look at high-temperature polymers, if you look back, there has been very limited selection of high-performance, high-temperature polymers on the market. And if you walk the show today, you will find some here and there. There's some FDM. We have something I'm going to talk about. But it's still limited. And if we move along, if we go more in production, those high-performance polymers have a big potential. So it's just a matter of time, and we're going to see a big increase in those as well. I'm going to give you a little introduction on that today. As our market is constantly growing, I have made the experience that there's usually some people in the audience who are fairly new to 3D printing. So I'm going to give a just brief overview of how our technology works, so we're all on the same page, as it's kind of the basics for the next information. So we use powders as materials, and we use lasers as an energy source to solidify the powder. And it all starts with a CAD model from any computer-aided design software you might have. That model is sliced on the computer into 2D slices that are being sent to the printer. And then the printer applies a layer of powder material, and the energy source, the laser, is melting the powder in the selected areas. And that continues layer by layer, so the platform is lowered by the thickness of a slice, and again, the recoater applies powder, the laser melts the powder in the selected areas until you have finalized your part, and then you unpack it, you can sift the powder and reuse the powder, and you end up with your final part. That's the process we have, and we call selective laser sintering, SLS. Now that brings a couple of advantages over conventional manufacturing. So the entire layer by layer additive manufacturing gives you the ability to design, or you can do bionic designs, you can save weight, you can save material. At the same time, it gives you the ability to customize or individualize objects. That's a great advantage in medical, for example, for any patient-specific implants. You just tweak the design file, so you don't have to tweak your entire production process. And that is why you have that flexibility to do one-offs, small series, and so on. And last but not least, you also have the ability to combine several parts in one, so integrate functionalities and reduce your part complexity, that again comes along with the advantage to do less assembly, less logistics, so save overall costs. Sorry. And one example I just want to point out, because it addresses more or less all of those advantages in one piece, is a pick-and-place part. It's a lightweight gripper. On the bottom you see the conventional design. It's a standard gripper with machined parts. On top you see the additive part. So it has been redesigned in a way that now those channels, or the structure itself, actually incorporates channels where the pressurized air goes through that operates the grippers itself. And what they have been able to do is to reduce the complexity of the part from 21 different parts to just 3 different parts by just integrating several parts into one component. And also the manufacturing time was drastically reduced from 18 days to just 1 day, as well as a significant reduction in weight and overall cost. And that's just when looking at the part itself. When you look at the entire system on where that part is being used, that is a gripper that is in use with a injection molding machine. So it takes the part out of the injection molding machine. And now with this new design, which is less high, they don't have to open the injection molding machine as far. So you have quicker turnover, you can do more cycles, you will save cost in your entire system. And also the gripper weighs less, so you can use a smaller robot that can actually also move faster. So you need to think beyond just the part when you look at the advantages of additive manufacturing. Now when we move on to the polymer world, I put here a couple of well-known polymer families we all see in our everyday lives, ranging from like PC and ABS that we have in the car interiors, but also any PE, PP materials that we have in the plastic bags we get at every supermarket, all kind of plastic containers. Those materials we see every day. Major thermoplastic material families. But those are not necessarily the ones we also see in additive manufacturing. Some of you might know, but maybe some others don't. So why is that? Why are those not the major families we also see in additive manufacturing? And to answer that question, I want to look at this pyramid of polymers that helps you understand. So it divides the polymer world in 2 halves. On the left-hand side, we have the amorphous polymers. On the right, you have the semi-crystalline polymers. And then it also has 3 different levels. You have the commodity polymers on the bottom, you have engineering polymers in the middle, and high-performance polymers on top. Now, when we look at additive manufacturing, and especially our process of selective laser sintering, we need certain crystallinity for our process to work. Amorphous materials turn out really porous. So if you highlighted in red the materials we have on the market today, so you see most of them are on the right side. Actually, except one, all of them are on the right-hand side. And the one that is on the left, the polystyrene at the bottom, that is being used for casting. So it's a green part, it's not a final part, it's really porous. So, okay, so let's stay on the right side of that pyramid. Now you don't see anything on the bottom. And that is because at the bottom we have the commodity polymers, and they are commodity polymers for a reason. They are really cheap, they're being used in injection molding for high volume, so it's really a market that we don't even address with additive manufacturing. It's a market where we don't see fit, that doesn't fit to our offerings. We target applications that have high value, and those high value applications usually need engineering polymers or high performance polymers. So today you see most of today's polymers are actually in the engineering section, and we have a lot that are based on polyamide 12. That's a well-known material in this additive world here. And it's a good material, but it has certain limitations. If we want to go to more demanding applications, we do need more performing materials. And that brings us to the top of that pyramid. where today we have a PEKK on the market. I'm going to talk about that as well. And many times people ask about PEEK or PEKK-like materials, so I cluster those in a polyaryl ether ketones, the PEKs. And those are on top of the pyramid, so keep that in mind. So that's today's picture. Question is, what is next, or what should we be developing next? And that is a question that has been asked in 2015 during a study that actually the outcome shows that high temperature polymers as well as carbon fiber reinforced materials are among the top priorities on what the additive market should be developing. Now that's great, but why is that? Why are people so interested in those materials? And I want to do that step by step. So first of all, why high temperature polymers? I touched on that a little before. And a very obvious reason is, okay, if you have a part that requires high use temperatures, you need a high temperature polymer. That's an easy one. But it's beyond that. It's also those high performance, high temperature polymers have the potential to replace metal components. At the same time, you save weight. So you have additional advantages. So, okay, let's say, okay, I have an application where I need a high temperature polymer. Now, which one of those? Why should we do this group I called PEKK? And if we look at this material family, they come with a lot of great properties that can be a good fit to the challenging environments or applications you might have. So they have a very good chemical resistance. They are resistant to gamma radiation. They are radiolution. That's of interest, for example, in the medical market. They have this inherent flame retardancy, which is one of the key drivers for any mobility application, aerospace, for example, and they have at the same time those very robust mechanical performances. So, okay, let's agree that this group of material is superior and we want to focus on that. But why should you now laser sinter it? Why not just manufacture it conventionally? And that really goes back to the advantages I pointed out in the beginning. So you do have that freedom of design that brings you to weight savings, to bionic designs. It gives you the ability to design really complex parts that you're not able to manufacture any other way. At the same time, there's cost advantages. You have no tooling. You can also, as I said, integrate parts, so you might save on logistics, assembly along the production. And you can have time savings, obviously. And one example I want to show here is this disc of a painting robot. That used to be a metal part, and they have redesigned it to be smaller, more lightweight, and a PEKK part, so the current material we have on the market. And it had to be one of the challenges in that case, it had to be resistant to all kind of cleaning agents and fluids, as it's in a painting robot. And that material can do that. At the same time, if you look there, it's more than 90% weight reduction compared to the metal parts. So again, you can use a smaller robot, you can move quicker, you have a lot of additional advantages around that. And if we want to compare on how this current material that is out there compares to any of the others, polyamide 12s and so on I mentioned, you can see if you plot the tensile strength and the modulus, on the tensile strength on the x-axis, it's very much on the right. It's a very hard and strong material, and also the modulus is in the upper range compared to all the other more general materials we see on the market. And that has a couple of successful applications today. I'm putting a range here. So again, this robot disc I was mentioning, but there's others like the manifold of a combustor high pressure turbine that again had weight savings for more than 70%. There is this impeller that is a design that is really close to impossible to manufacture out of metal any conventional way, and again has weight savings, plus this unique new design leads to better part performance. And other examples are from the motorsport, like any brackets to save space, to save weight again. Those are all applications requiring high temperatures or requiring the chemical resistance, while at the same time making use of all the additional advantages you can have from additive manufacturing in general. And those we see today, but moving forward, what will the future look like? And when we listen to the market and our customers, and as an example, point out aerospace here, they look for even higher performing materials. They need to be strong materials, they need to be lightweight, but they also need to be cost efficient. So if we look at those range of requirements we get from the market, I want to point out one or two. So one really interesting one is the improved isotropic properties. If you look back at how our process works, it's layer by layer. So it's just from the nature of the process, we have stronger material properties in X and Y than in C direction. That's just how the process works. But anyhow, our customers are asking us to come up with a material that has isotropic or close to isotropic behavior. So that's a challenge. Second one is just managing costs. So the current materials on the market are not, the one we have is not refreshable. So you have to dispose all the leftover powder, which makes it really cost intensive. So another request here is to really make this, close the gap to real production. You need to have a more cost-efficient material. So it has to be refreshable, what we call it. So you reuse the powder, you put new powder in, and you can you can reuse the mix of that powder. So those two requirements were really guiding us on finding an approach and how to address that. And our approach was, again, we looked at those PEKK materials for one reason, because they're on the right side of this pyramid, and all the other additional advantages I was pointing out. And we also decided to do a carbon fiber reinforcement to the material. It has multiple advantages. It adds to the stiffness, obviously, but it also reduces the coefficient of thermal expansion that has a positive impact on the shrinkage. And I will also get to the other, like the isotropic properties are very much linked to the carbon fiber reinforcement as well. I'm going to go into details. And we decided to encapsulate those carbon fibers. So you might, and by encapsulation I mean they are really encapsulated in the polymer particles that we put in the machine. So another alternative would be you just take the polymer powder, you take the carbon fibers, you mix it, tri-blend, and you put it in the machine. But what we did is we compounded it into the polymer particles, and you're going to see why that is, why that was our approach and what the outcome is. So if we look into outcomes of that exercise, you can see on the picture, it's a microscopic picture, and I'm going to have some more on that. On the right-hand side, you see there's the particles of the PEKK, and you see some carbon fibers in there, and they have a kind of chaotic orientation, and that really helps for the isotropic behavior of the material. On the left, I have this very basic but still little table that shows the relative values of X, Y, and C for the tensile strength and the modulus. And you see C is still not the same as X and Y, but it's pretty close. And if we look a bit more into detail into how those carbon fibers organize themselves in the parts, we did cross sections at different planes, the X, Y, X, C, and so on. If you look at those pictures of those cross sections, you can see the fibers are in all directions. And that was so that is a material we call HT23, and the 23 stands for 23% of carbon fibers we mixed with this PEKK material. Now, if we compare that to a tri-blend we did with just 10% of carbon fibers, so one that does not have those carbon fibers encapsulated in the powder, but just a loose mix of those, I have a picture on that here, and it's not so easy to see, but it's the XC plane. So the recoater would go this way, and the C direction is upwards. And you can see there's almost no fibers that are in the C direction. And that is because in the tri-blend, when you use your recoater and you're recoating the powder, you kind of force the carbon fibers to lay down. So you have hardly any fibers in the C direction. And that's just in comparison to what we see when we do encapsulate the fibers. We have it all directions. And that adding or the encapsulation of carbon fibers not only helps with the isotropic behaviors, but also improves the strength and the dimensional stability or the shrinkage of the final parts. And I compare here the HT23, so the carbon fiber encapsulated polymer, with a neat PEKK, so a PEKK without any carbon fibers. And you can see the tensile strength and the modulus increase. The elongation break decreases a little. That's just because it becomes stiffer and then the elongation goes down. And the shrinkage, it's in favor of the shrinkage. So you have less shrinkage because of the carbon fibers, giving it more stiffness as well. Still, we have very good detail resolution on the parts, which you can see a little bit on those pictures there at the bottom. Before I go into this. So I mentioned the refreshability as another criteria. I don't have any picture on that, but it turned out this PEKK material also it is refreshable. We did studies. Usually the powder sees certain damage when it's being exposed to this high temperatures for a long time in the machine. That leads to higher viscosity, and that you cannot always reuse the powder anymore. That's what we had with the current material. In this case, we did tests, aging tests and everything, and it does go up a little bit, but then it stays there. So it doesn't increase like linear. It just has a little bit of an increase in viscosity, but it still can be processed very well, and then that viscosity level kind of stays stable. That's a very good turnout because that helps us with the cost of that material. Now, that's the material development we did. But apart from having a material that suits the requirements of future production parts, we also need a machine, and we need just more than just a material. So in terms of machines, we have that vision that additive manufacturing really becomes an efficient way of production. And that's a picture of the R&D halls we have at the headquarters. So if you imagine that's a future customer site for high temperature polymers, then of course, machine-wise, we have a range of machines, but those specialty polymers require special machines. So we are at the very right of this machine portfolio. That's the machine we have today for the material that is available. And it goes up to 385 degrees Celsius. It's kind of unique in the market. And we're going to come up with a new version of that one as well that is targeted more to this carbon fiber reinforced material. Has some little changes, like a different recoater because of the carbon fibers encapsulated there. And when you set up, or when we talk about production, having a machine, having a material is great, but you really need to manage the quality along the entire supply chain. So what we do is we put a lot of effort into the pre-process, we call it. So any quality assurance we can do before you actually start production, that is where we put a lot of effort into. And it starts, one I want to highlight is the powder quality assurance, so the material itself. From batch to batch, you have slight variations, so we need to manage the quality along those material supply chains we have. And to do so, what we do is we have when we get powder in a pre-product, then we have an incoming inspection, obviously. We have a production control for the compounding of the carbon fibers and everything we do. And we also produce specimens for every material batch. So we do tensile bars, we pull the tensile bars, we compare on how that looks according to the database we have, and then you will get that overview, kind of a certificate of that powder batch every time. And that's really important when you think about production, and that's where we want to go. Apart from that, it's also the entire life cycle around everything. So setting up a production line, additive manufacturing isn't easy. I'm sure some of you have experienced that. And it starts with the installation of the machine, but then it's on training, on how can you make that work for you and your application? How can you maybe even tweak parameters so it fits better to what you need to do? And always look at this entire cycle of what needs to be done to be successful in production with additive manufacturing. And one last thing I want to look into is, except from that HT23 we now talked about, what else? Maybe you need something else. Maybe you need a neat refreshable material or a lightweight PEKK material or whatever. So we are set up in a way that we have EOS as the big mother company, basically, that is really focused on the industrialization. So anything in that, what I mentioned, in the production requirements, addressing those quality needs, improving the core technologies we use, making sure that machine to machine and everything is stable. But we also have ALM, which is part of EOS over here in the States, and they can help you individualize and differentiate if you want to. So based on the core technologies we have, based on all the experience we've built up, we can help to find a unique material or unique settings for whatever application it may be. But we do have that basis coming from EOS. And last but not least, why should you, if you want to go into high temperature polymers, why should you do that with us? We do have a long history in high temperature polymers. As I stated, we still have the one and only machine that really can do those very high temperatures with the selective laser sintering process. We have, apart from the polymers, also all the metals. We have all those trainings around the entire story and how you actually set up a production. And we have multiple engineers and consultants that can help you on the way there. So if you're interested in moving in that direction and differentiating yourself with high performance polymers, we are here to help you, and we have a booth over there. You should see it in that corner. You're welcome to join anytime and we can go into more details. But now, of course, I'm happy to answer any questions you might have right now on the spot. Thank you.
Got a mic here if anybody wants to ask a question.
Doesn't work.
It's not. No, there it is. If anyone's got a question, I can pass the mic. If Stephanie's be happy to answer a few questions. All right, here we go.
Can you elaborate a little on your carbon fiber encapsulation process? Are you doing the compounding yourselves? And when you recycle that, have you tested that in your quality program so that we still maintain the z-axis improvement in isotropic performance?
Yeah, so I can't go into specifics on how exactly we do it, but we do the compounding ourselves. And in terms of how that has an influence on mechanical properties, when you refresh or when you recycle the material, that's part of the study we did. We not just looked at processability, if it's in general possible to just reuse the remix powder, but we also pull tensile samples for after every aging cycle. And that showed that the mechanical properties, as well as the viscosity more or less, it has after the first. So if you start with a entirely 100% virgin new powder and you do the measurements, you have a certain value, and then you refresh it and you do your next cycle, then your viscosity increases a little bit and your mechanical properties decrease a tiny little bit. It was less than around about 1% maybe. So it was in a range that was really insignificant. And then after that, doing additional aging cycles, that did not get worse or did not increase. There is a paper.
Have you published?
Paper. I can look into if that's open to the general public. We can follow up on that.
Are there any other questions for Stephanie? All right, if there are no other questions, thank you very much, Stephanie. We appreciate your presentation.
Do I need to do anything with that?
Look at that.